Hello and welcome to my YouTube channel Curious Pharma. My name is Sai Teja. I am currently pursuing my masters in pharmacology and toxicology at Naipur Mohali. In this video, I will be discussing the important concepts of first order and zero order kinetics in pharmacology. As students in this field, it is crucial that we have a strong understanding of these fundamental concepts. So whether you are a student or a researcher in this area, this video will provide you with a comprehensive understanding of first order and zero order kinetics. So let's get started. First order elimination kinetics. It is also called exponential kinetics. In this, a constant fraction of the drug is being eliminated per unit of time. Refers to the phenomena of drug elimination in the pharmacology, where a fixed proportion of a drug is eliminated from the body from unit time regardless amount of the drug present in the body. Whatever amount of the drug that present in the body, it just eliminate constant fraction of the drug from the body. This is known as first order elimination, where the rate of elimination proportional to concentration of the uh, drug in the body. We can see with example. For example, see the 80 mg, you have given 80 mg into the body. 80 mg in 4 hours it will be converted into 40 mg. 40 mg in 4 hours 20 mg. 20 mg into 10 mg. 10 mg into 5 mg. 5 mg into 2.5 mg. Here constant fraction of the drug is being eliminated per unit time. Constant fraction 80 mg converted to 40 mg in it is 50% is lost in 4 hours. Constant from here also 40 mg to 20 mg lost. How much it is lost? 50% in 4 hours. This is what we call constant fraction of the drug is being eliminated in per unit of time in first order. The second thing is rate of elimination. As we already discussed, rate of elimination is dependent on and directly proportional to plasma concentration. More the plasma concentration, more drug will be the eliminated. For example, here is 80 mg of the drug. If suppose 160, same like more the concentration of the drug, more it will be eliminated. This is first order kinetics. And second thing is, the higher the amount, the more rapid the elimination. More the amount of the drug, more will be the it will eliminate the drug. And T off doesn't depend on dose of the drug. We can see with this example. You can see here first T off. What is T off or off life? Off life of a drug is defined as the time taken for the plasma concentration of the drug to be reduced by half. In first order kinetics, the half-life of the drug is constant and it is independent of initial dose or concentration of the drug. This means that plasma concentration of the drug will be reduced by half after a fixed period of time. Here we can see T of is constant. 4 hours. See, in 4 hours it eliminates 40 mg. Here also you can see 20 mg is eliminated in 4 hours. Like 80 to 20. How much time it takes to eliminate 40 mg of drug? 4 hours. 40 to 20, 4 hours. Here T of is constant. T of, it is a constant here. 40 to 20, 4 hours. 20 to 10, 4 hours. In 4 hours only it is eliminating. In zero order, the T of is constant. You can see, and fourth one is most of the drugs are first order except if you given a drug in very high dose. If you given a drug in very high dose, it will leads to saturation of transporters and it undergoes zero order kinetics. We'll learn about zero order kinetics in further slides. This is the concept of first order. We can see here first order analogy. When a candle is lit, it begins to burn. It begins to burn and releases the wax at a time that is proportional to heat generated by the flame. As the candle burns down, the size of the flame decreases and the rate of the wax releases also decreases. Following first order, like it's a similarly, like when a when a drug is administered to the body, it is metabolized and eliminated at the rate at which proportional to its concentration. As the drug concentration decreases, the rate of elimination also decreases. And why most of the drugs follow first order kinetics? Because most of the undergo first order, because their elimination from the body occurs at the um, rate proportional to concentration of the drug in the body. This means that a fixed fraction, it is in this is fraction is important in first order. Fixed fraction of the drug is eliminated per unit time rather than fixed amount. In zero order, fixed amount will be eliminated, whereas in first order, fixed fraction of the drug is eliminated. For example, let's consider the commonly used painkiller acetaminophen. When someone takes a standard dose of acetaminophen, the drug is absorbed into the bloodstream and distributed throughout their body. As the liver metabolizes the drug, it is broken down into active metabolites and eliminated from the body. The elimination of acetaminophen from the body allows first order. This means that the rate of at which drug is eliminated is proportional to concentration of the acetaminophen in the body. Like a constant fraction, always remember constant fraction of drug is eliminated per unit time rather than a fixed amount. See the graph of the order uh, first order kinetics is like exponential, as we discussed earlier, because the rate of process is proportional to the amount or the concentration of the substance. This means that rate of change is not constant over the time but rather decreases as the substance is consumed or transformed. For example, see 80 mg at 0, 40 mg. Here it is a plasma concentration of the drug versus time. In x-axis we took a time and y-axis we took plasma drug concentration. 80 mg at 0 time. When it converts to half T of to 40 mg, 4 hours. When 40 to 20, 8 hours. 20 to 10, 12 hours. So the curve is exponential, not linear. It is exponential curve. We can see exponential curve in first order kinetics. Now let's discuss zero order elimination. This means a fixed amount of the drug is eliminated per unit time regardless concentration of the drug in the plasma. Let's understand with example. For example, you can see 80 mg converted into 70 mg in 4 hours. How much it is lost? 80 mg. Constant amount is being eliminated per unit time. See 70 mg to 60 mg. How much it is lost? 10 mg. 60 to 50, 10 mg. 50 to 40, 10 mg. Constant amount in first order, constant fraction 50% there, but here constant amount in zero order, constant amount of the drug is being eliminated. And rate of elimination is independent of plasma concentration in zero order or saturation kinetics. whereas in first order rate of elimination is dependent of plasma concentration. We can see here every 4 hours 10 mg of drug were eliminated. See, every 4 hours only 10 mg, 10 mg, 10 mg, 10 mg. So it is independent of plasma concentration. How much it is, only fixed amount of the drug is being eliminated. That's why um, what we call only fixed amount is being eliminated from the body regardless the plasma concentration. And no fixed half-life, and T off is variable. In first order T off is constant, but in zero order T off is variable. Why? Let's see here. See, to here it is 80 mg. For 80 mg to 40 mg, how much time it takes? 16 hours. For 40 mg to 20 mg, how much time it takes? 8 hours. Half, to convert half of the drug 80 mg to 40 mg, that is what we call T off. How much time it takes? 16. Here 40 to 28 hours. See, that's why T off is variable. A small increase in the dose of in the dose, big increase in the concentration. For example, uh, imagine we gave 20 mg instead of 80 mg. We have to wait extra 16 hours until the drug is eliminated here. When see when zero order will occur, when the transporters or enzymes are saturated. What is this saturation? Enzymes can become saturated when the rate of substrate, example, consider a drug metabolism exceeds the capacity of enzyme to metabolize. This occurs because enzymes have finite number of active sites that binds to substrate molecule, and once all the active sites are occupied, enzyme enzyme can no longer have any more metabolite. As result, the rate of metabolism becomes constant, and zero order, and that is what we call zero order kinetics. And a small increasing the dose of a drug, big increase of concentration, as we seen earlier. See, here we can see the analogy. Imagine a classroom with a door that can only allow a certain number of students to enter per minute, regardless how many students are waiting outside. As each student enters the classroom, and other students is allowed in at a same rate. This is similar to zero order elimination, because the body eliminate a constant amount of a drug per unit time regardless concentration of the drug in the body. See, there are three example. I have taken three example of drugs that exhibit zero order elimination at a higher concentration, which increases risk of toxicity. Firstly, alcohol. Alcohol, a classic example of a drug is that exhibits zero order elimination is alcohol. When you given high concentration, when a person drinks heavily, their liver enzymes responsible for metabolizing alcohol can become saturated, resulting in zero order elimination. This leads to accumulation of high levels of alcohol in the blood, which can cause a range of toxic effects such as impaired judgment, motor coordination, and breathing, and can even be fatal in extreme cases. Second is phenytoin. Phenytoin is an anti-epileptic drug that is known to exhibit zero order elimination at a higher concentration. If a patient taking too high of dose of phenytoin, or if their liver enzymes are responsible for metabolizing drug become saturated, the drugs can accumulate in the body and cause toxic effects like dizziness, nausea, vomiting, and even seizures. Aspirin, as we know, it is a non-steroidal anti-inflammatory drug, NSAID, that can exhibit zero order elimination at high dose. When a patient takes high dose of aspirin, the enzymes responsible for metabolizing the drug can become saturated, leading to zero order kinetics. This can result in the accumulation of high levels of aspirin in the body, which can cause toxic effect such as stomach ulcers, bleeding, and even drug kidney failure. The concept of, as we know, that the concept of enzyme saturation is important in pharmacokinetics because it can affect the clearance of the drug from the body. When the enzymes are not saturated, the clearance of the drug is proportional to the concentration of the drug, and follows, see here, first order kinetics. In this case, increasing the dose resulting proportional like increasing the dose um, resulting in proportional increasing the rate of drug and metabolism and elimination. However, when enzymes become saturated, see here, enzyme, when you give high substrate, enzyme becomes saturated, the clearance of the drug from the body is no longer proportional to concentration of the drug, and drug follows zero order elimination kinetics. In this case, increasing the drug dose can result in increasing the risk of toxicity. Okay, here you can see in a zero order only constant amount of his drug is eliminated, so that's why it is called linear decay, whereas in first order it is exponential decay. In zero order it is linear decay. It is plasma concentration of drug versus time. Constant amount of the drug 70 mg in 4 hours, 60 mg, like only 10 mg is being eliminated for every 4 hours. It is linear decay. See, when we want to convert um, log into, like, for example, 10, 90, this is the plasma concentration of the drug and this is the time. If you want to convert exponential graph into linear, we'll go with natural logarithm. We have to add logarithm. When we add logarithm, it will be, it look like this. This is the no logarithm. When you apply no logarithm, it looks like 190, 80. But when you apply logarithm, it converts to like this. Why we have to apply logarithm, we'll discuss in next slide. See, converting an exponential graph, this is the first order elimination, to linear graph, this is the linear graph, is useful technique in pharmacology, as it allows pharmacologists to analyze the pharmacokinetics of the drugs more accurately and make more informed dosing decisions. Pharmacokinetics is a study of how drugs are absorbed, distributed, metabolized, and excreted by the body. One of the common application of this technique is in determining half-life of a drug. The half-life is the time required for the concentration of the drug in the body to decrease by half. That is what we call like half-life. In pharmacokinetics, the half-life of the drug is the important parameter. It determines how often the drug must should be administered to maintain therapeutic levels in the body. To determine half-life, pharmacologists often use drug concentration in blood over the time, and they plot the data on an exponential graph. This graph, however, this can be difficult to interpret results, like as exponential graph have a changing rate of change. To make it easier to visualize and analyze the data, the pharmacologists convert exponential graph to linear graph by taking natural logarithm on both sides. As we discussed earlier, I have shown you we applied logarithm, how it look like. If you apply logarithm, log concentration, it converts to linear, so we can interpret results easily. See, this is graphic analysis. This is what we call zero order elimination or else saturation. This is how the graph look like. Whereas first order elimination, this is plasma concentration of the drug versus time. This is exponential graph. It is a first order. Here we are converted into exponential graph to linear. Why we are converting exponential to linear? In order to estimate, in order to interpret or estimate any pharmacokinetics parameters like T of easily. Linear graph we can estimate or interpret very easily. So we converted into log concentration. When on the y-axis, if it shows log concentration, it is first order graph, first order elimination, log concentration versus time, whereas zero order plasma concentration, no logarithm is applied here but log function is applied here. That's the difference. Thank you guys. If you like my video, please hit that like button, subscribe to my channel. This is Teja signing off.